It's important that you understand that carbon-carbon double bonds found in alkenes are rigid. What that means is that they do not exhibit rotation or free rotation around that double bond. So say, for example, if we look at a molecule like ethane, I'll try to draw it in 3 dimensions here with the dashes and wedges. So let me put a dash here and a wedge here. And it's important that you understand that there is free rotation around this carbon-carbon single bond. I can move that bond, I can rotate it around and spin it. But when I have a carbon-carbon double bond, so let me just draw an alkene here with a carbon-carbon double bond. So I'll draw 2-butene, and we'll talk more about how to name this properly in a bit. But what's important is that you understand that there is not free rotation around this bond. It cannot happen. Okay, and the reason why is because of the orbitals that are involved in forming that bond. And what we're going to see is that because this cannot happen, that we get what are called cis-trans isomers. And these are isomers that are different only in the way the atoms are arranged in space. And in order for cis-trans isomers to exist, there's a requirement, which is that we have 2 different groups on each of the carbon atoms attached by the double bond. So what that means is, say for example, this carbon involved in the double bond, it has 2 different groups attached to it, right? It's got the proton or the hydrogen attached to it, and it has the methyl group attached to it. And the same thing holds true for this carbon attached to the double bond. It has a hydrogen and a methyl group. So that's one of the requirements that has to be met in order to have cis-trans isomers. It says here that 2-butene is the first example of an alkene which can have 2 different structures based on that restricted rotation about the double bond. So let me show you what I mean by that. So if I draw my carbon-carbon double bond, okay, now in 2-butene, I have my methyl group, then I have a carbon with a hydrogen, and I have another methyl group like this. But you can probably already imagine that there's another way to arrange these atoms in space. So if I put my methyl group here and I put my hydrogen down here, what if I swap those on the second carbon like this? Well, in this case, what we're dealing with now is we have 2 different molecules. So the one that's on the left, the 2 methyl groups are on the same side of the molecule. You could say the same thing about the hydrogens, and we would call this cis-2-butene. And the second molecule, I'm sure you can already guess that since the 2 methyl groups are on opposite sides of that double bond, or the 2 hydrogens are on opposite sides of that double bond, we call this trans-2-butene. Now these are both 4-carbon alkenes, so they both have the same molecular formula, right? Both of their molecular formulas are C4H8, right? Following that CnH2n rule for an alkene. So they both have the same molecular formula. They're even connected in the same way, right? It goes from a methyl group to a carbon with a double bond to another carbon involved in the double bond and then another methyl group. What's the difference between these 2 molecules? The difference is that because there is no free rotation around the carbon-carbon double bond, you cannot interconvert between these 2 molecules. Impossible. Okay, so they're geometric isomers, which means they're isomers. They have different shapes or different geometries overall. And we have a fancy word that we use for these, and we call them stereoisomers. And we'll talk about that more in a little bit. Here's another example of 1,2-dichloroethene, and you can see that I have 2 geometric isomers. I have cis 1,2-dichloroethene and I have trans 1,2-dichloroethene. They both have the same molecular formula, C2H2Cl2. Exact same molecular formula. Again, they're even connected in the same way. Right? One carbon has a single bond to hydrogen and a single bond to chlorine. The second carbon has a single bond to hydrogen and a single bond to chlorine. And of course, the 2 carbons are attached by the double bond. What's the difference between them? The difference is, if I look at that double bond, in the first molecule, the 2 chlorines are on the same side of the molecule. And when they're on the same side, we call that cis. In the second molecule, the two chlorine atoms are on opposite sides of the molecule, or opposite sides of the double bond, and we call that trans. Now for these examples, I circled the chlorines, but the same thing could be said about the hydrogens. In the first molecule, both of the hydrogens are on the same side of the molecule, and in the second molecule, the hydrogens are on opposite sides of the molecule. Before we move on, I just want to show you one kind of interesting thing here, is that this molecule that I have drawn down here in black also has the same molecular formula as the two molecules on top. But if one of the two carbon atoms of the double bond has two identical substituents, which both of these carbons do, the first carbon has two identical atoms, right? The two hydrogens. The second carbon has two chlorines. Those are identical. When that occurs, there are no cis-trans isomers for the molecule. And the reason why is that in order for us to use cis or trans in nomenclature is that if I'm using cis, I have to have two groups that are identical on the same side of the molecule, just like as is shown here with the two chlorines or the two hydrogens. You can see that that is not the case here. If I look at the top face or the bottom face of this molecule, I have a hydrogen and chlorine on both faces, and therefore they are not the same atom, so cis or trans doesn't apply. I have that point written down right here. It says that if one end of the carbon-carbon double bond has two groups that are the same, cis and trans isomers are not possible. Both of the carbons of the carbon-carbon double bond must have two different groups attached in order for us to be able to apply cis and trans. Now, in order to apply cis and trans properly in nomenclature, you have to find a group common, that means the same, on both ends of the carbon-carbon double bond. Again, if the common group is on the same side of the pi bond or the double bond, the molecule is cis. If they're on opposite sides of that double bond, the molecule is trans. Let's take a look at this example here. Each carbon has two different substituents. You can see that on the carbon on the left, I have a methyl group and a chlorine. And on the carbon on the right, I have a chlorine and an ethyl group. So that works out. But we also note that one substituent on each carbon is the same, and that is the chlorine. And you can also see that the chlorines are attached on opposite planes of that double bond, and therefore they will be trans. So let's give naming this molecule a try. Since it's an alkene, the first thing we're going to do is we're going to number the longest carbon chain, giving the double bond the lowest possible number. So that would be like this: 1, 2, 3, 4, 5. Since the double bond begins on carbon 2, this must be some kind of 2-pentene. Now I have a chlorine at carbon 2 and at carbon 3, so this is going to be 2,3-dichloro-2-pentene. And finally, since the chlorines are on opposite sides of that double bond, I have to designate the molecule as trans 2,3-dichloro-2-pentene. Let's decide whether each of the three compounds in this slide is cis, trans, or neither. If we take a look at the first one right here, you can see that I have a carbon-carbon double bond and that I have two methyl groups, one on each of the carbons. So the criteria is met that I have two groups that are identical on each of the carbons and they're on opposite sides of that double bond. Therefore, this would be a trans double bond. Looking at the example on the right over here, you can see that this is neither cis or trans because I have two groups, two isopropyl groups that are the same on one of the carbons involved in the double bond. So we'll put neither for this one. And finally, for the one at the bottom, it doesn't matter if you're looking at the hydrogens or if you're looking at the ethyl groups. Since the hydrogens are on the same side of the molecule, or you could say the ethyls are on the same side of the molecule, this molecule is cis. Later on in this class, we'll study lipids in detail. And fatty acids are lipids that are actually just long-chain carboxylic acids found in vegetable oils. and they can also be found in animal fat. The fatty acids found in vegetable oils have unsaturation, just like is shown here in oleic acid. You can see that since these two hydrogens are on the same side of the molecule, which is blown up down here, this is a cis fatty acid. The geometric isomer of a cis fatty acid would be a trans fatty acid or a trans fat. Trans fats do not come from natural sources, meaning they don't come from plants or animals. You might be asking, well, where do trans fats come from? Well, trans fats are actually a byproduct of what we call hydrogenation reactions. And the reason why trans fats get such a bad rap in terms of diet is because they have been reported to lower levels of good cholesterol, which we call HDL, or high-density lipoprotein. So far, we've looked at isomers just in terms of molecular formulas. We've looked at geometric isomers. Now it's time to look at a new kind of isomer, what we call a stereoisomer. And I alluded to this earlier on in the video, in that stereoisomers are isomers that differ only in the 3D arrangement of atoms. So cis and trans isomers are technically stereoisomers. And you should also know what constitutional isomers are. And constitutional isomers differ only in the way the atoms are bonded to each other. If you look down at the bottom of the screen, you can see that all of these molecules, 1-butene, cis-2-butene, and trans-2-butene, are all constitutional isomers. Why? Because they all have the same molecular formula, C4H8. And you can see that cis-2-butene and trans-2-butene, not only do we call them geometric isomers, but we can call them stereoisomers because they differ only in the three-dimensional arrangement of atoms, or the way the atoms are arranged in space. Again, the molecules cis-2-butene and trans-2-butene are both connected in the same way. It's just the orientation or the relation of the atoms in space that makes these two compounds different.